Hey guys, as you can see, today we're going to be talking about Newton's method, which is from chapter 3.8 in your calculus textbook. So basically what Sir Isaac was doing this time in his life when he came up with his this method is that he was trying to find out a technique that would use tangent lines to approximate the zeros of a function. So to see how this works, let's consider a function and its graph. And so this function is continuous on an interval, and it's also differentiable. And so let's say we have this function right here, and so in the interval we know we're going to have, due to intermediate value theorem, we're going to have at least one x-intercept. So drawing the tangent line through that x-intercept, you would choose that the x-intercept right here is what you want. So this x-intercept right here, where you're going to guess what the value is of it, because you don't know exactly, which is the point of this. So on this interval, if a, or the function at a and b differ in sign, as they do. One at a it's positive, at b it's negative. Then by IVT, there has to be at least one zero within a and b. So looking at this, we have a value where there's a tangent line of the function, which is x1, and we have an actual x-intercept over here, which we'll call x2. So using the point of the tangent, or the tangent line's equation in point-slope form, we can solve for the x-intercept that we're trying to find right here, x2, by using the point-slope form. So the point-slope form of the tangent equation. So y minus f of x equals f prime of x1 times x minus x1. And so right now we're actually proving how Newton's method works. This is not the actual steps, just to clarify. And so by the definition of an x intercept, we'll let y equal 0. So putting everything to one side, or sorry, yeah. We'll divide our y is equal to 0, so you divide, we're going to divide out f prime of x1. So we have negative f of x1 over f prime of x1 equals x minus x1. And so solving for x, which is what we want, right? Or sorry, this should be x2, my bad. solving for x2, we get x2 equals x1 minus f of x1 over f prime of x1. And this equation is what becomes the new estimate, which becomes a further specific, or more and more specific as time goes on. So x3 would equal x2 minus f of x2 over f prime of x2, and so on until you reach usually what is 3 decimal points after, 3 decimal spots after 3 spots after the decimal. So starting with the steps of Newton's method, first you're going to want to estimate what is x1, which is close to the c you're trying to find. So let's say you see something that looks near 1.5 on a graph. The point looks near 1.5 on a graph, so you're gonna, your x1 would be 1.5, and after that you would determine what the more specific approximation is using the equation x to the n plus 1 equals xn minus f of x n over f prime x sub n. And this equation used over and over again will give you a more and more specific approximation, as we already proved previously. So next, after that, after you have done this enough times, which are called iterations. Iterations is every time you go through the steps to get to the desired accuracy. And so by determining that accuracy, you have to do the absolute value of x sub n minus x sub n plus 1. And if that's how accurate you want it to be, x sub n plus 1 will be the final approximation. And if it's not what you want, then you can go back to step 2 and keep on doing iterations. So let's start off with a really simple example. Say we're given a function x squared minus 5, and usually you'll be given, if you're not given a graph of the function, unless otherwise stated, you will be given the x1. So in this sense, the x1 given was 2.2. And the problem says to do 2 iterations of this, and as we know, that will require doing the equation twice. And to organize all your information, the best way to do it is to create a table of your values, and it's going to be a 6-column table consisting of n, x sub n, f of x sub n, f prime of x sub n, f over x sub n, f of x sub n over f prime of x sub n, and the equation that we use, which is x sub n minus f of x sub n over f prime of x sub n. And by doing this, we can not mess up and completely organize what we need to find out. Also, obviously, to solve for f prime sub x sub n, you need to be able to figure out what f prime is. So you have to perform the derivative real quick. And so for this one, it's real simple. F prime of x is just 2x. So first you're going to need a calculator for this. Most of the time you will need one. So we know n is 1 because we're starting off with x sub 1. So what you'll put in for the x sub n is the number that x sub n is, which right now x sub 1 is 2.2. So first we're going to do f of x sub n, which is 2.2 squared minus 5, and that is negative 0.16. And continuing, the second one is easy. You don't need a calculator. It's just 4.4 because it's 2 times 2.2. And negative 0.16 over 4.4 is 0.036364, or we'll just 3636. And so 2.2 minus negative 0.03636 is 2.23636. So 2.236 becomes x sub 2. So n is 2, and it's 2.23636. So using this new x sub n, we're going to square it. Minus 5, we get 0.001322, and 2 times the x sub 2 is 4.47273, and f of x sub 2 over f of x, or f prime of x sub 2 is 0.00296. And finally, x sub 2 minus f of x sub 2 over f prime of x sub 2 is 2.23636 minus 2.23606. And we're going to truncate this, which is cutting it off, not rounding it. We're going to cut it off after the third. And we already did 2 iterations. The number right here will tell you how many iterations you've done. And so we'll say x sub 2 equals, or sorry, 2.236. And that is all that is necessary. So sometimes Newton's method fails, and this is usually when it cannot produce a convergent sequence, which means that the sequence is converging or coming upon a certain x value. Usually this means that it's does not exist because f prime of x sub n equals 0, because we know that in the using the equation to solve x sub n minus f of x sub n over f prime of x sub n, if the denominator is 0, then it can't exist. In the spirit of Sir Isaac, regards. See you guys next time.